Have you ever wondered how the electromotive force, or EMF, in a DC machine is calculated? This question might seem arcane to some, but for those who have delved into the world of electrical engineering, it's a crucial part of understanding how these machines function. The EMF, a fundamental concept in electromagnetism, is the energy provided by a source per unit charge. On the other hand, DC machines, whether they are generators or motors, are the workhorses of the electrical world. They convert electrical energy into mechanical energy, and vice versa, through the principles of electromagnetism. Understanding the EMF equation of a DC machine is not only a stepping stone to mastering the operation of these machines, but it's also a gateway to unlocking many other concepts in electrical engineering. So, fasten your seatbelts and prepare to dive into the world of electromagnetism. Today, we'll unravel the mathematics behind the EMF equation of a DC machine. The EMF equation of a DC machine is not as complex as it seems. Let's dive in and break it down. The equation, represented as E equals V minus Ia times Ra, might seem like a jumble of letters at first, but each of these symbols has a unique significance in the operation of a direct current or DC machine. Starting with E, this represents the back or counter electromotive force, also known as EMF. In a DC machine, this is the voltage generated by the machine itself when it's operating as a motor. This back EMF opposes the supply voltage and is a crucial aspect of the machine's operation as it balances the motor speed. Next, we have V, which stands for the supply voltage. This is the external voltage provided to the DC machine to start its operation. It's the driving force that gets the machine going. Moving on to Ia, this represents the armature current. The armature is the rotating part of the machine, and the current flowing through it, the armature current, plays a significant role in determining the machine's torque or rotational force. Lastly, we have Ra, symbolizing the armature resistance. This is the inherent resistance offered by the armature winding to the flow of the armature current. It affects the efficiency of the DC machine, as higher resistance means more energy is lost as heat. So, when you look at the EMF equation, E equals V minus Ia times Ra, it's actually describing a balance of forces within the DC machine. The supply voltage drives the machine, countered by the back EMF. The armature current and resistance further influence this balance, affecting the machine's speed and efficiency. Understanding the EMF equation allows us to predict and control the performance of DC machines. By manipulating the supply voltage, armature current, and armature resistance, we can optimize the machine's operation for different applications. So, in essence, the EMF equation gives us a way to calculate the back EMF in a DC machine. It's a powerful tool, not only for understanding how these machines work, but also for harnessing their full potential. Now that we understand the EMF equation, how does it apply in real-life scenarios? Let's consider a few practical applications where the EMF equation is utilized. One of the most common uses is in controlling the speed of a DC motor. By adjusting the voltage and current within the motor, we can effectively control its speed, ensuring precision in a wide range of industries from manufacturing to automotive. Another crucial application lies in electrical power generation. Power stations use the principles of the EMF equation to generate electricity, converting mechanical energy into electrical energy. Here, the EMF equation helps us understand the relationship between flux, the number of coil turns, and the speed of rotation in the generator. These are just a couple of examples, but the EMF equation is a cornerstone in many other electrical and electronic applications, from charging your smartphone to powering space explorations. As you can see, the EMF equation of a DC machine has wide-ranging applications in the field of engineering. Let's recap what we've learned about the EMF equation of a DC machine. We began by introducing the concept, delving into the crucial role it plays in the world of electrical engineering. This equation, which relates electromotive force, flux, speed, and the number of conductors, is the backbone of understanding and controlling direct current machines. We then broke down the EMF equation, exploring each component in detail. By understanding the relationship between these variables, we can manipulate the operation of DC machines to our advantage. We also touched on the practical applications of the EMF equation. From electric vehicles to industrial power tools, The EMF equation is everywhere, silently powering our daily lives. And that wraps up our discussion on the EMF equation of a DC machine. Remember, a good grasp of this formula can make a huge difference in your engineering journey.